So the second option is we're going to use it for the second notebook, which is really kind of a quick refresher on, I think for most of you, just a refresher on Pandas and GeoPandas. I forgot, who is not familiar with GeoPandas? But most of you are familiar with Pandas as such, so I'll go pretty quickly over that then. So this second way of opening notebooks is using Visual Studio Code. If you do any kind of serious programming, I would strongly recommend that. So I have it set up here. It's I have the folder open that has all the notebooks in it. So if you don't have that ready to go, you need to go to that folder or whatever. But it's the same. So this is the first one that we just did. And now I'm going to do the second one. So if I click on it, there it is. Okay. So you see up here, you have this select kernel thing. The first time you open this notebook, Visual Studio Code doesn't know what you're actually using. So if you click on this, you see, I happen to have Julia installed here, and I have different Python environments. So I'm going to go to the Python environments and pick PY312, which I just customized with all the packages that I use. So you see, I have a bunch of other environments and other versions of Python that I could choose from. This is very flexible type of thing. And so now we're in business. We have, if you forget to do this and you try to load the modules, it's not going to do anything. Okay. Can you read this okay, or should it be larger? Okay. Yeah. So this is the second notebook, and I always give a little introduction, what it is that we actually do in this notebook. So this is very basic. We're going to use a different sample data set, one called police. So make sure if you don't have it loaded that you import libpycel, because I don't actually import it here. I only import the get path part of libpycel, but if you don't have it installed, import libpycel and then use libpycel examples, load example police, and then it will be available to you. Okay. And you can of course use any other data set. It's pretty generic. So these are the imports. We NumPy, Pandas, GeoPandas, and then, as I mentioned a few minutes ago, in order to avoid having to write this libpycel examples whole thing, I import from libpycel examples, I import get path. Okay, so now I only have to write get path, not the whole specification, right? So I'm going to go again. There's a couple of different ways to run the cell in Visual Studio Code. You can do control return, or you can go here and run it with this little simple, you see it actually says you can do control enter. So make sure it's active and then do control enter, and it loads all the modules that you need. And so what we're going to use is a bunch of different things, but you're probably familiar with this, so I'm going to go fairly quickly. And if there's something you're a little rusty on, you can always revisit it and take another look. So array, shape, toList, reshape. Reshape is a very important one. I use it all the time to make sure that the outcome of an operation is in the format that I want. And this is something that can be a little confusing in the beginning if you work with NumPy. I know it threw me off in the beginning in that a NumPy array of one dimension doesn't have a second dimension. So it's not a column vector or a row vector. You know, a row vector would be number of rows and one row and number of columns. A column vector would be number of rows and one column. So they have two dimensions. A matrix in NumPy has two dimensions. An array only has one dimension. And so then for certain things, it doesn't matter, but for other things, it does matter, and it matters very much. So then you really want to know whether it's a column vector or a row vector, and you want to specify that. And we do that by means of reshape. So I use reshape all the time to make sure that what I have is a column vector, because that's typically what I use. These are a bunch of Pandas things, how to read it, how to get the contents, how to do descriptive statistics, correlations, how to turn it, make a data frame from an array, and how to put two data frames together, dropping variables, write it out to a CSV file. The reason I'm using this particular example, the police example, is to illustrate Pandas. I use a CSV file and not a shapefile. And then get path is here, okay? So the files that we use are actually, again, our 4 shapefiles for police, the CSV file that has the same data, but in a comma separated format, it's a text file, and then a GeoJSON file, which is an alternative spatial format. In the open source world, they really poo-poo shapefiles, and shapefiles are actually not that great. Shapefiles are optimized to draw maps. They're not optimized to do things like spatial searches. They don't have a sophisticated spatial index. Spatial index is something that gets you find things in 2 dimensions very efficiently, instead of having to go all the way around before you find it. So those kinds of things are built into the more modern data structures, you know, which are most of the open source databases now have spatial capability because of this geometry column. That is a real innovation. And so things like DuckDB, which is a very powerful database system, has a spatial add-on, and you can do all kinds of really fancy searches on really large files in DuckDB that there's no way you can do in ArcGIS or anything like that. Okay. So this is, again, my way of doing things. Everything is set up generically up on top here. If you want to run this with your own file names, you just change the file names up here, and everything else remains the same. So I'm loading this. Make sure you do this, otherwise it's not going to work. So first the CSV, and we use Pandas to read CSV to know where it is. Again, it's a sample data set, so it's on your hard drive under application support. It's sitting there, nowhere not necessarily in your working directory or anything like that, but it doesn't matter because you can find it with the get path. So you get the path here, and then you read the CSV file using that path. And then again, we're going to print the shape of it, and we're going to print the top of the data set. So I believe what you can do is you can go this way. So you see what is different between this example and the shapefile that we just looked at in the previous notebook. Look at the last column. There's no geometry. This is just a text file. It just has the data. It has nothing spatial. It's not a spatial file. That's why we read it with Pandas. Pandas doesn't know about space. Only GeoPandas knows about space, okay? So, you probably know all this, but just as a refresher, I'll go over it very quickly. I'm not going to read everything. So the most generic way to find out what's in a Pandas data frame is to do info. And info gives you this technical stuff, what class it is, the range, the index, the range of the index, basically, how many observations do you have? Every variable is listed, and it says what it is, right? It's integer or float or anything else. So, yeah.
Do we have the police CFC installed?
You have to install it.
Oh.
That was your assignment at the bottom of the page of the first notebook. Install police. So you install it. If you don't have it, make sure you import lib by cell. Just open a new cell.
Okay.
Add a cell. You know how to do that?
Yeah.
Okay. So import lib by cell, and then do this command here. Lib by cell, examples, load example, police. And then you have it. Okay. So where are we? Okay, info is the most generic one. And there's the reason I spend a little time here, because this has a couple of gotchas, you know. These are all different ways to do the same thing. But the outcome is a different type of object. So sometimes it's a list, sometimes it's just a generic Pandas index object, which is basically not usable by anything else but pandas. And then sometimes it's an array. So you have to, if you're going to use these variable names for something, for example, to extract subsets of variables, you have to use the right type. So this first one is the list of the data frame. You see this is a list. There's just the names of the variables. This looks exactly the same, but it isn't. It's an Pandas index object. So it looks like a list, but it isn't a list. So if you manipulate or you try to manipulate it as a list, it's not going to work. These are the values of the columns and they become an array. So this is a NumPy array. This is not a list, even though it looks like a list, it's not a list, right? And then this takes that array and turns it into a list. So this one also looks like a list, but this one is a list. Okay, so I call these gotchas. If you don't pay attention, you know, you're working with the wrong thing and it's not going to work, right? Or worse, it's going to do something that you don't recognize and it messes up your results later on. So descriptive statistics is describe, and it gives you the mean, the standard deviation, the minimum, the maximum. Did I ask this in this class? I know I asked it in my other class. Who's familiar with Tobler's first law of geography? Of course. Okay. Everything is related to everything else, closer things more so. It's a notion of spatial autocorrelation and a notion of distance decay. We'll talk a little bit about that as part of the boot camp later on. But Tobler had another law, and he never wrote it down as a law, but Tobler would always say, do the descriptive statistics and specifically look at minimum and maximum. Because it is so easy to have data errors. This is a pet peeve of mine. The quality of your input data determines the quality of your results. Garbage in, garbage out. And it wouldn't be the first time that somebody typed an extra zero in a percentage. So you end up with a percentage that is 250, and it should be less than 100. Or you end up with a percentage that's negative for some weird reason. Your minimum and maxima will always pick that up. So this is one of my golden rules. Always look at the descriptive statistics first. Not so much because you necessarily want to know what the mean is, but you want to know if there's anything funky with these variables. Also, if you have a lot of missing variables, it will pop out. You know, you're loading a data set, it's not yours. You're really interested in a variable, and then it turns out that variable is in there, but it doesn't have any data. And you run into this a lot when you go to open data sources. You know, like cities put these data on their website, half of the variables have no information in them, right? And this is how you find out. So getting a variable, I'm assuming everybody knows how to do this. Here's another gotcha. You need 2 brackets. If you only put 1 bracket, it's not going to work. This doesn't create, it's a way of looking, of pulling variables out of a data frame. A more elegant way, and it avoids a lot, again, it makes things, you can make it totally generic, and this is what we're going to do with the regression code. You specify the variable names in a list, and then you pull them out. So now we have a little data frame, right? And then, of course, when you only have 2 variables, it's much more meaningful to do descriptive statistics. And you do correlation. Maybe you're not that familiar with this. They have a simple correlation coefficient. So one thing that we will do a few times, but much less than in legacy. I mean, I shouldn't say legacy. SPReg before 1.5. So before 1.5, what you had to do in SPReg is turn everything into a NumPy array first, and then pass those as arguments. You recall the cheat sheet from last week, where you have all the arguments for each regression command. You saw Y and X. In the old days, Y and X needed to be NumPy arrays. Now they can be data frames or data series. So this you actually don't need to do explicitly, but you still need it. So it's a very simple transformation between a data frame and a NumPy array. It's done by NumPy. It's simply the way you create an array in NumPy, and one of the arguments that is allowed nowadays is a data frame or a data series. So now we have a NumPy array. And then I just wanted to show you, and if you're familiar with Pandas, this is going to go really fast. I'm computing, just as a simple illustration, the complement of the variable college. Variable college is for each county, the percent of people who have a college degree. And so I just flip it around, the percent who don't have a college degree. And here's the gotcha. So I used the column in what was an 82 by 2 matrix to create a new thing. This is not a column vector. This is a NumPy array. See, there's no second index. Now, you may know this already, but if you don't, this will get you in a lot of trouble if you don't know this is going on. For some things, it won't matter, but for other things, it will give you outcomes when you expect to have a scalar, a single number as the outcome. It may be a huge matrix, and you don't know why. This is why, because this doesn't know what shape it has. So then my trick is reshape -1, 1. This makes it into a column vector. And then, where are we here? So now if I look at the dimension, it does have a column dimension. It's exactly the same thing. Nothing has changed to the numbers, but now it is a column vector. And now I can concatenate it. Now, some concatenation works fine when you don't have the second dimension, but it's living dangerously. So my preferred approach is always force it to something that you know what it is. If you want it to be a row vector, make it a row vector by reshaping it. If you want it to be a column vector, make it a column vector by reshaping it, okay? Don't let the assumptions work against you because it can get you in trouble. So we can create, so a few cells ago, I made an array from a subset of a data frame. Now we're going to flip it around. Now we have an array and we're going to turn it into a data frame. And that's the data frame, what else? Function. You pass it an array. Okay, I just made this an 82 by 1 column vector. And we give a name to the columns. If you don't give an explicit name, it will give a name for you. You typically will not like the name it gives for you, right? And then then the second thing, so here we're in Pandas, right? Before we were in NumPy. NumPy made an array out of a data frame. Now Pandas makes a data frame out of an array, and then we will slap the two arrays together. So this is our original one that doesn't have non-college, and this is the one with just non-college. This is very important because you can slap them together horizontally or vertically. So adding columns versus adding rows. If axis is 1, you add a column. If axis is 0, you add rows. So I believe, don't quote me on this, but I believe the default is 0. That's probably why I have it here as axis 1. So then we do this, and there we go. We have non-college added to our data frame. Now, if you've done this before, it's no big deal. Specifically, we will be using that to add predicted values and residuals to our original data frame. So that's kind of the routine that we're going to be using. And so then you can write this to a CSV file, right? My preference is to set index false. Index is like an additional column, and CSV doesn't really know how to deal with it, right? And so when you set index is great internal to Pandas because it gives Pandas its efficiency in finding rows, finding columns, and all that stuff. But outside of Pandas, it can be very confusing. So I get rid of it when I write it to a CSV because you don't need it. When you read the CSV, Pandas create the index anyway. So you don't really need it. Okay. So then a little bit of time on DBase files. Who has not worked with DBase files before? Okay. That's a good thing because it's an old standard. It's actually out of date in the opinion of most people, right? But it was the original format that ESRI used for its ArcGIS software. It holds the data. There's a couple of things about DBase that you should know. The worst one is that the longest variable name can only be 10 characters. Now, if you grew up in the world that I grew up in, that's no big deal because we were forced to have very short variable names. But nowadays, people write long variable names with spaces in them and underlines and dots, and DBase doesn't know how to deal with that, okay? So 10 characters, it's a limitation. That's why if you use GeoJSON or something like that, you don't have to worry about it. If you're going to use shape files, you have to worry about it. So what often happens is you read a CSV file, for example, with X and Y coordinates, and you want to turn it into a map of points. Right? You have the X and Y coordinates, you can make it into points. But if you do it into a shape file, some of the variables in your CSV file that may be more than 10 characters don't go into DBase. And then you have to change their names or do all kinds of weird stuff to get it to squeeze into the format. And sometimes it's not that easy because you say you have a variable name, underline, and a year. And that goes beyond 10 characters. So where are you going to chop it off? If the year is 2010, 2012, 2013, and you chop it off after 20, they're all the same, right? And that's another gotcha that you have to watch for. So for good reason, I think, I don't know, but I suspect Pandas does not support DBase files, okay? They're basically telling you, don't mess with that, right? But GeoPandas does. But GeoPandas does because of the shapefiles, because the shapefiles have their data in DBase files. So GeoPandas can read a DBase file, Pandas cannot. Okay, so if you want to read a DBase file, you can use a specialized package. There is one, I think it's called Simple DBF, but you don't have to. You can read it with Pandas. But there's a catch. Okay, Pandas thinks it is part of a shape file. So if the DBF file is in a directory, in a folder, that also has the other parts, SHP, SHX, it will read the geometry column. If it is in a folder without the other stuff, it will not read the geometry column. So if it is in a folder with other spatial files, it will become a GeoPandas data frame. If it's by itself, it becomes a Pandas data frame. This is really bizarre. I didn't know this either. I just found out the hard way, right? So if you do this, we check the DBase file, and you see it becomes a GeoPandas GeoData frame, and it has the geometry column. Even though we only read the DBF file, we didn't read the shape file. Okay, so it shouldn't know that this is a spatial thing, but it does. Okay, and then look what happens. So I'm going to drop the this is how you drop columns in a GeoPandas and Pandas, and then it became a regular data frame.
Is that a version of GeoDatabases, or is it something different?
It's different. It's its own. DBase used to be a database software company. And so there was DBase 3, DBase 4, DBase 5. I think they went out of business. Or actually, I think they were acquired by something else. And I don't believe it's supported anymore, but it's a legacy in ArcGIS. And if you use ArcGIS, you will know that they're pushing you to use the GeoDatabase instead of the shapefiles for good reason, right? So as I mentioned, all the modern spatially enabled database system like PostGIS, which is Postgres with a spatial component, DuckDB has it, Polars, which is another one of those fancy new ones, has a spatial extension. They don't use shapefiles. They don't use DBF. They have their own optimized internal data structures. And so if you do anything serious with big files, like, I mean, my wife's RA, right? So she happens to have a file that is 70 gigabytes large, okay? my laptop, not this one, this is my toy laptop. My real laptop has 64 gigabytes of memory. So that does not compute, right? Well, in DuckDB, I was able to load that file and pull out the observations just for Chicago, which are still a couple of thousand, but not 80 gigabytes. So if you have to work with really large data sets, DuckDB is your go-to tool. And it is spatially enabled. So then you can do all kinds of spatial queries like distances, next to, within, radius, buffers, and all that kind of stuff. I will not talk, I may mention it again a couple of times because I'm really enamored by it, but we will not be using DuckDB, okay? So you cannot write a DBF file with GeoPandas. So it's kind of a hack. You know, if you really want to work with DBF files, you should use simple DBF. I purposely did not include that in my import list because I don't want you to work with DBF files, right? I would leave them alone. Read the shapefile in GeoPandas and then work with it within Python. It's no longer DBF. You know, it is an internal data structure, a Pandas data frame data structure, which has nothing to do with the source of the data. Once you get it into Python, it becomes an object that is manipulated internally, right? So you can't write a DBase file, but you can write it as a CSV file. If you want to do that ever, you can. So then I have a few more minutes. GeoPandas is for reading spatial data files. GeoPandas is very smart. It can figure out the format by the file extension. So we get the path to our shapefile, we pass it to read file, and we have our shapefile, right? And now it's exactly the same as before, but relative to what the CSV file that we read, it now has the geometry column, which allows you to do spatial queries. And then you can do new variables just like before. You can, I mean, if you're rusty on this, by all means, practice. If this is easy peasy, don't worry about it, right? And just to show you the flexibility, the up here on top, if you recall, where am I? Okay, so I had in-file shape was the police shape file, and I have in-file geo, which is police GeoJSON. If you load the example, you know, take a look at that file. It's a text file. GeoJSON files are really, they're kind of a superset of JSON, which stands for JavaScript object notation, but it's really has very little to do with JavaScript, actually. It's just historically. So we don't say anything about this. We just say in-file geo. It knows that it's a GeoJSON file. It knows how to translate the contents of that file into a GeoData frame, which is a data frame with a geometry column. So it's exactly the same thing as before. So here we go. You can't tell the difference. It looks exactly alike because it is exactly alike. Remember what I said, the source doesn't matter. Once it's inside Python, inside Pandas or GeoPandas, it becomes a GeoPandas data frame object with its own functionality, its own methods, its own attributes, nothing to do with the source. Now, if you then want to write it out, again, depending on the file name that you give, it writes it in a particular format. So you don't even have to tell them, I want to write this as a shapefile, or I want to write this as a GeoJSON file. If you put the file extension SHP, it writes it as a shapefile. If you put the file extension GeoJSON, it writes it as a JSON file, GeoJSON file. So Go wild, check out the data sets, and if you know this stuff, fine. I just want to make sure, as I mentioned on Monday, I want to make sure everybody's on the same page. You know, some of you have more GIS skills than others. Some of you may have more regression and econometric skills than others, but I want to make sure we're all at the same point. Basically, my target is end of next week, maybe the beginning of the one after, and then we're off to the races in the spatial world. Okay. So that's it for today. I'm going to close the recording.